Okay, everybody, welcome to the wireless channel. Today we will hear a talk by Mohammed Hatami in cooperation with Yang Tang Nguyen and my old colleague Marco Junti from the Center for Wireless Communications at the University of Oulu in Finland. And the talk will be about energy efficient waveform design and subcarrier allocation for multi-carrier MIMO joint communication and sensing systems. Welcome, Mohammed. Thank you very much for being there. We are all here very interested in hearing you. So let's jump right in.
Okay. Thanks, Giuseppe, for the introduction, and it's a great pleasure for me to be here. And today I will present my paper entitled Energy Efficient Waveform Design and Subcarrier Allocation for Multicarrier MIMO JCAS, which has been done with my colleagues in the University of Oulu. And my name is Mohammed Hatami. I'm a postdoctoral researcher from University of Oulu in Finland. As you know, ISAC, or I mean Integrated Sensing and Communications, or Joint Communications and Sensing, have a lot of benefits. To name some, it can enhances resource efficiency and performance by doing joint signal processing, or it can increase spectral efficiency by using the same spectrum for both radar and communications. And it can also leads to reducing the hardware cost by using the same hardware for both sensing and communications. What we are interested more is that we can do both sensing and communication by using the same waveform. On the other hand, with the growing demand for energy conservation, energy efficiency has become a key performance metric nowadays. Therefore, in this paper, we focus on maximizing the energy efficiency by optimizing the waveform and subcarrier allocation in a multi-carrier system. In our system model, we consider a multi-carrier MIMO joint communication and sensing system where the transmitter it detects Q sensing targets while providing downlink communication service for U single antenna users. And we consider multi-carrier systems with K subcarriers. And regarding subcarrier allocation for sensing and communications, we consider two subcarrier allocation strategies, namely overlapping and non-overlapping. In the overlapping scheme, we use all the subcarriers for the communication and only use a subset of them for sensing. And in the non-overlapping strategy, we use some of the subcarriers for the sensing and the remaining for the communications. Therefore, the set of sensing and subcarrier, sensing subcarrier and communication subcarriers are disjoint. And we consider a SINR metric for both radar and communication to evaluate the performance. Regarding the communication model, which is a multi-user MISO system, we can have the received signal at each user as given by 1, which can be rewritten as 2. And in this equation, in equation number 2, as you can see, the first term is the desired signal, and then this term is the multi-user interference, and the last term is the noise. Therefore, we can calculate the SINR for each user at each subcarrier at given by 3. So the numerator is the power of the desired signal, and then the denominator is the total interference plus noise. And this is in each subcarrier. Therefore, we can calculate the overall SINR for each user over all communication subcarriers as given by 4. And for each subcarrier allocation strategy, we can calculate this SINR at given by 5 and 6 here. In 5, as you can see, for the overlapping scheme, since we use all the subcarriers for the communications, we do this summation over all the carriers. But in the non-overlapping scheme, we only sum the power over those that use for communication. Vk is the indicator that we use if subcarrier k is used for sensing, Bk is 1. Therefore, 1 minus Bk is the indicator that shows whether subcarrier k is used for communication or not. Having defined the SI and R, therefore, we can define the energy efficiency, which is the ratio of the throughput divided by the total power consumption. As you can see here, the energy efficiency is defined by 7, which is in the numerator, we have the sum rate over all the users, and in the denominator, we have the total power consumptions. The first term is the power for data transmitting, and the second term is the circuit power consumption, which is the power consumptions by RF chains, cooling systems, and etc. Regarding the radar model, which is a MIMO radar, the received signal at the radar receiver at each subcarrier is given by 8. So as you can see here, and in this equation, as mentioned before, we have considered a MIMO radar, and we have multi-carrier system. Therefore, for each target, we have MKL different samples from each target. Therefore, we should combine these MKL samples in such a way that maximizes the SI and R. Therefore, we need to also design the filter at the receiver of the radar. Assume that WQK shows the coefficient of this filter. Therefore, the output of this filter is given by 11. And in this equation, the first term here shows the desired echo power returned from the target Q. And the second term is the echo power received from other targets. So we can call it like interference. It's not exactly interference, but it behaves like interference. And the last term is the noise. Therefore, we can define the sensing SI and R as given by 12, which is the ratio between the total echo power from the desired target divided by other terms in the previous equation. So we can have this SI and R for the radar for each target Q as given here, which can be rewritten in this vector form. Note that the effect of the noise and interference is encapsulated in this R tilde Q. Having defined the SI and R for both communications and sensing, now we can define our problem formulation, which is maximizing the energy efficiency by optimizing the TX waveform X, the radar RX filters for each target, WQ, and subcarrier allocation vector B. And we need to also ensure that we satisfy the radar SI and Rs to make for the communications, to guarantee the communication for each user. Then we also need to guarantee the sensing so that we consider this constraint 13B and C. And 13D is the power constraints. The next two constraints are regarding the subcarrier allocations. And then the last one is due to the filter at the receiver to make sure that the coefficients of the radar receiver filter are finite. First, we design this RX filter, and we do it for, we fix the TX waveform and subcarrier allocation B. Then the problem of finding this RX filter coefficients is equivalent to solving an MVDR problem, which is given by 14. And it has been shown that the solution of this problem has a closed form as shown in 15, where alpha is a normalization factor. We can calculate this alpha from these constraints. Then by replacing this W in the SINR formula, then we can have the SINR formula as given by 16. As shown here, SINR formula, it it's a linear combination with respect to the subcarrier allocations, but it's non-convex with respect to X, because R also depends on X, and R inverse here make this non-convex. To design the waveform and subcarrier allocations, in which we need to find a solution to this problem 17, we use alternating optimization, in which we design the waveform and subcarrier allocations alternatively. First, we fix one of them and find the other one, and then fix the other one and find the first one, and then we do it until convergence. For the waveform design, we fix the subcarrier allocation, so we consider that it's given by B, and then the waveform design subproblem is given by 18. So this problem is in non-convex. To deal with this non-convex problem, we do as the following. First, note that 18B is convex constraint, and 18B can be rewritten as this 19, which is convex, which is what we need to deal with this non-convex constraint and non-convex objective function. To handle the non-convex objective function, we first use Dingelbach methods to rewrite the problem as in 20. Then we, as shown here, f1x is a summation of the log of some fractions. So we can use an equivalent formulation for this one, as shown in 22, where tau is an auxiliary variable. And we can iteratively update these auxiliary variables, and then we can find a solution for this problem, as shown here. So to just sum up for the waveform design, we find a waveform design by iteratively, and in each iteration we solve this convex sub-problem as shown in 26. So the objective function, we have used Dingelbach methods and sum of functions of fractional programming to deal with that one. Therefore, we handle the objective function as shown here. And then we rewrite the radar constraints by using successive convex approximation. So we use the first order Taylor series to rewrite the SINR for the radar as shown here, which is, we only replace the SINR for the radar by its first order Taylor series. Then we can iteratively find a solution for this problem. Regarding the subcarrier allocations, as mentioned before, we have to do it for both overlapping and non-overlapping. As mentioned in the beginning of this talk, for the overlapping, we use all the subcarriers for communications. Therefore, the SINR for the communications does not depend on the subcarrier allocation. And therefore, the energy efficiency also is independent of subcarrier allocations. In this overlapping scheme, we select the subcarrier allocation strategy to maximize the minimum radar SINR over all the targets. This problem is an mixed integer convex problem. Therefore, we can find an optimal solution by using exhaustive search, which has high computational complexity and running time. To deal with this, we relax the binary variable bk to continuous one, and therefore we can find a solution for subcarrier allocation by solving these convex linear optimizations, 27. At the end, since the solution is continuous, we only select the j largest entry of this vector b, which is the output of this problem, as sensing subcarriers, because we only need to select j of them. For the non-overlapping scheme, we can rewrite the problem as shown here in 28, which is mixed integer non-convex optimization problem. To deal with this objective function, which is non-convex, we can use the same method that we have used for the waveform design to deal with this. I mean, we can rewrite this objective function by using fractional programming, which is shown in 29. So we replace this objective function by this 29, in which omega is an auxiliary variable, and we iteratively needs to update this variable. Therefore, we find the solution for subcarrier allocation in the non-overlapping scheme iteratively. And this is the overall alternating optimization algorithm that we have used to find joint waveform and subcarrier allocations. We start with fixing the subcarrier. So we have chosen an initialization for subcarrier, which is uniform here. And then we fix the subcarrier and find the waveform design there. Then we fix the waveform and find the subcarriers and do it iteratively until convergence. And let's go to have some results and discuss on the results. These are the parameters that I have considered for the simulation scenario. We have considered 10 antenna elements and the transmitter, 6 antenna elements and the receiver of the radar, 10 subcarriers, 3 users, 16 time slots, and the center frequency is 1 gigahertz with the bandwidth is 100 megahertz. And you can see the rest of the parameters here. And we also consider 3 targets located at these angles and these location beams. And regarding the communication, we consider 16 QAM modulation scheme and Rayleigh fading model for the channel. It's worth noting that the method that we have introduced in this paper, it can be used for other modulation schemes and also channel models. So this is just an example that we have used in the simulations. And we compare the results with a baseline scheme in which we maximizes the communication sum rate instead of energy efficiency. In this plot, we shown the energy efficiency with respect to the total circuit power, P0, as shown here. As you can see here, when we increase P0, I can back to this energy efficiency formula so that I can explain better. Yeah, here. When we increase this one, it will be dominated. Therefore, this PD does not have any effect. So the performance of our metric would be close to the case when we only maximize this numerator. So as you can see here, yeah, when we increase P0, the performance of the proposed scheme in which we maximizes the energy efficiency, it will be very close to the case that we only maximizes the communications throughput. Next, we plot this figure, which shows the energy efficiency performance with respect to the radar SINR requirements. And it's clear that when we increase this gamma Q, the constraint would be, the feasible set would be reduced. Therefore, we need to have more powers to meet the radar SINR requirements. Therefore, we need to increase the power, which leads to decrease in the energy efficiency. And overall, we, as shown here and also in the previous figure, the non-overlapping scheme has a slightly better performance compared to the overlapping. To summarize, in this work, we have considered joint waveform design, subcarrier allocation, and radar receiver filter for energy efficient joint communications and sensing. And we have considered 2 overlapping and non-overlapping subcarrier allocation strategies. And we aimed at maximizing the energy efficiency subject to power constraints and communication and radar SINR constraints. And the problem was mixed integer non-convex fractional programming, in which we have used alternating optimizations with quadratic and Dingelbach transformations along with SCA to find a solution. And the numerical results shows the improvement of our scheme compared to the baseline. And also it has been shown that the non-overlapping scheme is slightly better than the overlapping. Thanks, and I'm here if you have any questions.
Thank you very much, Mohammed. Very interesting talk. I have a question, but I will hold it and first ask the audience if there are any questions. Any questions, guys?
So maybe I can ask a couple of questions. If you go
Sure.
to your simulation parameters in the previous part, yeah, here. So you say that you are using a carrier frequency of 1 gigahertz and a bandwidth of 100 megahertz. So
Yes.
is there any justification for this? I mean, this carrier frequency is really low. Usually for radar, at least you need, for communication scenarios, let's say it's okay because it's usually around 4 gigahertz or so in normal sub 6 gigahertz channels. But for radar, it's actually supposed to be at very high, at least 28 to 26 to 28 gigahertz, right? So
Yeah.
is any justification for this? And I'm also not so sure if you can use this much bandwidth at such a low carrier frequency. So any comments on this?
Yeah, actually, I have just chosen these parameters to do the simulations. So there is not such limitations on the scheme. So we can choose any center frequency and bandwidths, and we can run the simulations. And I cannot say that the results would be the same, but the thing that I can say that the method that we proposed still works. So, and second comment is that my background is mainly on communications, so maybe I'm not very familiar with the radar things. So yeah, you are right. For the radar, the center frequency is 1 gigahertz is very low. Yeah.
Okay, and maybe just one more quick question. So you say your communications channel follows the Rayleigh-Fady model. Are you using a different channel model for the radar part? Because if you're using the same waveform, then the channel should also be the same, right? So what's the justification for saying that you're using the communication channel as Rayleigh? And so what are you using for the radar, basically?
Yeah. Actually, for the radar, I have used line of sight channel because mainly the targets are line of sight channel to the transmitter. This is what we have considered for the radar. But as I mentioned before, the method that we have proposed, there is no limitation. So we can change these things and rerun the simulations. And we have only considered this one because they are very common in the literature. To consider line of sight for the radar and the fading channel for the communication. It's a common model. So we have also considered this common model to do the simulations. Yeah, thanks.
Any other questions, guys? Not, I have one. And it also goes back to the simulation scenario, but it goes a little bit closer to the problem you're trying to solve. And then my question is that you consider that you have only 3 users and also not so many, only 10 subcarriers. In a more realistic system, you probably are going to have a lot more subcarriers. And here comes the question. Have you considered a greedy version of this whole thing? Because we know that typically if the number of users is very large and the number of subcarriers is very large, the number of users is typically not that large because the number of subcarriers is there for another purpose, is just to do multiplexation, right, and achieve high rates. And which means that my hunch is that if you were to reconsider the problem in a scenario where K is really reasonably large, as it is in typical FDM systems with, I don't know, thousands of carriers, then maybe a greedy approach will come very close to the optimum at a fraction of the cost. That's my question. Have you thought about that?
Yeah, actually, the reason for using this number is obvious that there is due to the timings, because I wanted to submit the paper and I couldn't wait like months to have some results. So I have considered these numbers to have some results to submit the paper. This is the main reason. And I've changed this K not to 1000, but I've tried to do some optimizations on the codes so that it will be much faster, but not thousands. So I can increase K into like 64 or like 100 or something like that, but not more than that, because if I increase it more than that, maybe I should wait like for months to have results. But you are
But that's
right. Maybe a greedy approach for that scenario that we have thousands of subcarriers, it should work close to the optimal.
yes.
But I didn't think about that. I didn't think. Thanks for the comment.
Yeah. Okay. Any other questions, guys? Comments?
And
For me.
one more thing, Giuseppe.
Yeah. Go ahead.
Yeah. Typically, the number of carriers, it should be like thousands. Yeah.
Yes.
Okay.
Okay. All right. Thank you very much, guys. Yeah, and we can continue the discussion with Mohammed offline.
Yeah. Yeah. Sure.